Hello everyone. Today we will study the dot product. What is a dot product? First of all, keep this idea in mind. Note, in general, the dot product is used to measure distance and angles in a vector space. In general, the dot product is used to measure distance and angles in a vector space. Keep this idea in mind. Now next, let me define dot product in R3. Dot product in R3. Let A equal to A1, A2, A3, and B, vector B equal to B1, B2, B3. Let vector A and B be two vectors in R3. The dot product of vectors A and B is defined as vector A dot B equal to A1 times B1 plus A2 times B2 plus A3 times B3. So for dot product, we multiply the corresponding components, then add them up. For dot products between two vectors, we multiply the corresponding components, then add them up. This is dot product of A and B. Next, let's do a simple example. Let vector u be 1, 3, -2. Vector v be 0, -2, and 4. And vector w be 3, 2, 1. Find the dot product u dot v and v dot w. Let vector u be 1, 3, -2, v be 0, -2, 4, and w be 3, 2, 1. Find the dot products u dot v and v dot w. For u dot v, in vector u and v, we multiply corresponding components, then add them up. 1 times 0 is 0. 3 times -2 is -6. -2 times 4 is -8. Add them up. 0 plus -6 plus -8 is -14. Then for v dot w, same thing. In vector v and w, we multiply the corresponding components, then add them up. 0 times 3 is 0. -2 times 2 is -4. 4 times 1 is 4. Add them up, we get 0. So the dot product between vectors v and w is 0. So here we can see that the dot product of vector uv is a real number. And the dot product of vector vw is also a real number. So keep it in mind that for all vectors A and B, the result of the dot product A dot B the result of the dot product A dot B is always a real number. The dot product of any two vectors is always a real number. Next, let me show you some properties about dot products. Let A, B, C be vectors in R3. And let real number K be a scalar. First property, the dot product A dot A is always the same as the magnitude of A square. Dot product of A dot A is always the magnitude of A square. How does that work? Suppose A is the vector A1, A2, A3. We know that magnitude of vector A by Pythagorean theorem is square root of A1 square plus A2 square plus A3 square. That's magnitude of A. How about the dot product? How about A dot A? A dot A, we have vector A is A1, A2, A3. Vector A again is A1, A2, A3. When we apply dot product, we multiply the corresponding components and add them up. A1 times A1 is A1 square. A2 times A2 is A2 square. A3 times A3 is A3 square. Then add them up. We get A1 square plus A2 square plus A3 square. Then, if we compare the dot product with the magnitude, we can see that if I square the magnitude, I get A1 square plus A2 square plus A3 square, which is exactly the same as the dot product. That's exactly the same as the dot product. So that's the first property, that for any vector A dot A is always magnitude of A square. Furthermore, keep this idea in mind. The dot product A dot A is always greater than or equal to 0. The dot product A dot A is always greater than or equal to 0 because it's A1 square plus A2 square plus A3 square. Perfect square is always positive. Positive number plus positive number plus positive number is positive. It's greater or equal to 0. And furthermore, if the dot product is 0, then what happens? If the dot product of A dot A is 0, then what? Then vector A must be 0. If the dot product A dot A is 0, then vector A must be a 0 vector. If the dot product A dot A is 0, then vector A must be a 0 vector. Why is that? If the dot product A dot A is 0, that means A1 square plus A2 square plus A3 square is 0. They are all perfect squares. Perfect squares are greater than or equal to 0. Every term here is greater than or equal to 0. If their sum is 0, that means they must all be zeros. Since every term here is greater than or equal to 0, if their sum is 0, that means every term must be 0. So A1 square must be 0. A2 square must be 0. A3 square must be 0 if their sum is 0. Then we have A1 equal to 0 if I take square root. A1 must be 0. A2 must be 0. A3 must be 0. if all components are 0. If every component in vector A is 0, then vector A must be the 0 vector in R3. If every component in vector A is 0, then vector A must be the 0 vector in R3. So keep it in mind. If the dot product A dot A is 0, then A must be the 0 vector. That's the first property of dot product. Next, for any vectors, A dot B is always the same as B dot A. For any vectors, A dot B is always the same as B dot A. This is called the commutative property. This is called the commutative property of dot product. That means when I switch two vectors, the dot product is the same. If I switch two vectors, the dot product is exactly the same. Next one, A dot B plus C. For any vectors, A dot B plus C, that can always be written as A dot B plus A dot C. This is called a distributive property. When I have A dot B plus C, I can distribute vector A to B and C. This is called distributive property. Next, for any scalar K times A dot B, K times A dot B is the same as Ka dot B. It's also the same as A dot KB. That means if we have a scalar K times the dot product, I can either take K, multiply to the first vector, or take K, multiply to the second vector. Answer is the same. So when we have a scalar K times the dot product, I can either multiply K to the first vector or K to the second vector. Answer is the same. Next, if I take 0 vector dot A, no matter what A is, answer is always 0. If I take 0 vector dot A, then no matter what A is, answer is always 0. Those are the properties of dot products. You can verify each properties by letting vector A equal to A1, A2, A3, vector B equal to B1, B2, B3, vector C equal to C1, C2, C3. Then in each equation here, verify that left side equal to the right side. In each equation, verify that left side equal to the right side. So I'll left the verification part for you. Verify each of them by yourself. Next, let's do some simple examples using these properties. First example, let U be a vector in R3. And let K be a real number. Let scalar K be a real number. Show that the magnitude of Ku is the same as the absolute value of K times magnitude of U. Let's prove it. So for magnitude of Ku, if I square the magnitude of Ku, then by the first property, if I square magnitude of Ku, I can write it as dot product of Ku dot Ku. That's the first property. If I square the magnitude of a vector, I can write it as a dot product of this vector by itself. Then by property number 4, if there's a scalar multiplied to a vector, I can pull the scalar to the front. If there's a scalar multiplied to a vector, I can pull the scalar to the front. So I can pull both scalar to the front. I can pull this K to the front, pull the other K to the front. If I pull both k to the front, I have k times k times u dot u. And we know that k times k is k squared. U dot u, by first property, dot product of a vector dot itself is the magnitude of the vector square. So u dot u can be written as magnitude of u square by first property. So here we know that magnitude of ku square is k squared times magnitude of u square. If I take square root on both sides, since magnitude is always positive, so I get magnitude of ku. Then square root of k squared is absolute value of k. Square root of k squared is absolute value of k. Square root of magnitude of u squared, since the magnitude is always positive, so when I take square root, I get magnitude of u. And that's the proof for this. Next example, let vector u equal to 1, 2, negative 2, and vector v equal to negative 4, 2, and 4. Find the magnitude of vector u, v, u plus v, 2u minus v using dot product. First of all, how do we use dot product to find magnitude of u? Think of the first property. If I square magnitude of u, I can write it as vector u dot vector u. If I apply dot product to vector u, I have 1, 2, negative 2 dot 1, 2, negative 2. Apply dot product here, I have 1 times 1 2 times 2 is 4, plus negative 2 times negative 2, which is also 4. 1 plus 4 plus 4 is 9. Then since magnitude of vector u square is 9, by taking square root, magnitude of vector u is 3. And similarly, magnitude of vector v, I first of all take square, then using the first property, magnitude of vector v square is vector v dot vector v, and we know that vector v is negative 4, 2, 4. Vector v is negative 4, 2, and 4. If we apply dot product here, we have 16 plus 4 plus 16, which is 36. Then for magnitude of vector v, I take square root. This is magnitude of vector v square. For magnitude of vector v, I take square root. Square root of 36 is 6. Next, how do we find the magnitude of vector u plus v? So I first of all write it as magnitude of u plus v square. Take square root in the end. By the first property, magnitude of vector u plus v square can be written as the dot product of this vector. We consider vector u plus v is one vector. So apply the first property, I have u plus v dot u plus v. That's the first property. We consider u plus v is one vector. Apply the first property. Square of the magnitude is the dot product of the vector by itself. Then apply property 3, the distribute property. Apply the distribute property. We have u dot u plus u dot v plus v dot u plus v dot v. U dot u, vector u dot u by first property is magnitude of vector u square. U dot v and v dot u, they are exactly the same by property number 2. U dot v and v dot u, they are exactly the same. So combine these two terms, I can write it as twice u dot v. Combine like terms for these two terms, I have twice u dot v since they are exactly the same. Then v dot v, by the first property, that's magnitude of v square. We know magnitude of u square is 9. Magnitude of v square is 36. Then for dot product u dot v, we can compute here. Vector u dot v is 1 times negative 4 is negative 4. 2 times 2 is 4. Negative 2 times 4 is negative 8. Multiply the corresponding components and add them up, I get negative 8. So the dot product u dot v is negative 8. Now I plug in. Magnitude of vector u square is 9. Dot product u dot v is negative 8. Magnitude of vector v square is 36. 9 plus negative 16 plus 36, that's 29. Then for magnitude of vector u plus v, we take square root. That's square root of 29. Next, the magnitude of vector 2u minus v. In order to use dot product for the magnitude, I first of all square the magnitude. Then by the first property, we treat 2u minus v as one vector. Apply the first property, I can write it as the dot product of this vector by itself. I write it as 2u minus v dot 2u minus v. Then apply distributive property. Apply distributive property, I have 2u dot 2u plus 2u dot negative v plus negative v dot 2u plus negative v dot negative v. That's distributive property. Then for negative v, I can consider negative v as negative 1 times vector v. For negative v, I can consider this is negative 1 times vector v. Then I can pull out coefficients by property number 4. When there's a scalar multiplied to a vector, I can pull the scalar out. When there's a scalar multiplied to a vector, I can pull the scalar to the front. By property number 4, I can pull scalar to the front. So pull out both tools. I get 4 times vector u dot u. Next term, I pull out 2. Pull out negative 1. I get negative 2 times u dot v. Next, pull out negative 1, pull out 2. I get negative 2 times vector v dot u. For the last term, I pull out negative 1, pull out negative 1. I get positive 1 times vector v dot v. Then by the first property, vector u dot u is the magnitude of vector u square. That's the first property. Vector a dot a is magnitude of vector a square. So u dot u is magnitude of vector u square. And then by property number 2, we know that u dot v and v dot u are exactly the same. U dot v and v dot u are exactly the same, so I can combine like term. But that's negative 4 times vector u dot v Then last term, v dot v by the first property is magnitude of vector v squared. Then plotting the values. We know that magnitude of vector u squared is 9. Dot product u dot v is negative a. Dot product u dot v is negative a. Magnitude of vector v squared is 36. Magnitude of vector v squared is 36. Then combine like terms. 4 times 9 is 36. Negative 4 times negative a is negative 32. It's positive 32. Plus 36. We have 104. That's the square of the magnitude of 2u minus v. Then in order to find the magnitude of 2u minus v, take square root. Square root of 104 can be written as 2 square root of 26. That's the magnitude of vector 2u minus v. Next, let's look at a theorem here. Let A and B be two vectors in R3. And let theta be the angles between vectors A and B. Let theta be the angle between vector A and B. Then the dot product of A and B equal to magnitude of vector A times magnitude of vector B times cosine theta. Theta is the angle between vectors A and B. How do we prove it here? Let me show you a simple picture first. Assume that's vector A and that's vector B. If I connect both heads together, I have another vector. If I join both heads of the vectors, I have another vector here. What's this vector? What's this vector? Let's call the unknown vector vector x. Let's call the unknown vector vector x. Then we know that vector b plus vector x is vector a. If we consider vector b plus vector x, we shift the tail, put the tail of vector x to the head of vector b, then connect from initial tail to the final head. This is vector a. Vector b plus vector x is vector a. If we try to add two vectors, we shift the tail of vector x to the head of vector b, then connect the initial tail and the final head. That's the resulting vector, which is vector a here. So vector b plus vector x is vector a. Then if I solve this equation for vector x, subtract b from both sides. Vector x is a minus b. So this side is vector a minus b. This side is vector a minus b. And this is angle theta. Theta is the angle between vector a and b. Now, do you remember the law of cosine? Law of cosine says for any triangle with sides A, B, C assume the angle between side AB is theta. Then we have a squared plus b squared minus 2ab cosine theta equal to c squared. Assume c is the side opposite to the angle theta. Then c squared equal to a squared plus b squared minus 2ab times cosine theta. This is called the law of cosine. If we apply law of cosine here, C, in this picture, C is this side, which is magnitude of AB, magnitude of A minus B squared. C is magnitude of vector A minus vector B. And C squared is magnitude of vector A minus B squared. A is this side, which is magnitude of vector A. So that's magnitude of vector A squared plus B. B is this side, which is magnitude of vector B. When I plug into the formula, I get magnitude of vector B squared minus 2ab. A is magnitude of vector A. B is magnitude of vector B times cosine theta. So by law of cosine, assume this side C, so we have magnitude of C squared equal to magnitude of vector A plus magnitude of vector B minus twice magnitude of vector A times magnitude of vector B times cosine theta. That's law of cosine. Then we try to simplify this formula. Magnitude of A minus B squared, by the first property of dot product, this can be written as A minus B dot A minus B. That's the first property of the dot product. We treat A minus B as one vector. Then simplify this. If I distribute, I have A dot A minus A dot B minus B dot A plus B dot B. Then we know that vector A dot A is magnitude of vector A squared. Vector A dot B is the same as vector B dot A. So I can combine like term like that. What is negative 2 times vector A dot B. And vector B dot B is the same as magnitude of vector B squared. That's the left side. That's the simplified left side. Now carry the right side down. If I bring the right side down, I have magnitude of vector A squared plus magnitude of vector B squared minus 2 times magnitude of vector A times magnitude of vector B times cosine theta. Then in this equation, I can cross out magnitude of A squared on both sides. I can cross out magnitude of B squared on both sides. If I cross out magnitude of A squared and B squared, what's left is negative 2 times the dot product A dot B equal to negative 2 times magnitude of vector A times magnitude of vector B times cosine theta. Then I can divide both sides by negative 2. I get magnitude of vector A dot B. So I got vector A dot B equal to magnitude of vector A times magnitude of vector B times cosine theta. And that's the proof of this theorem. And for the previous theorem, always keep one idea in mind. The previous theorem can always be rewritten as cosine theta equal to the dot product a dot b over magnitude of vector A times magnitude of vector B. In this formula here, I can always divide both sides by magnitude of vector A and B and get cosine by itself. So the previous theorem can always be written as cosine theta equal to vector A dot vector B over the magnitude of vector A times magnitude of vector B. And we usually use this formula to find angle between two vectors. We usually use this formula to find angle between two vectors. Now, for angle between two vectors, be very, very careful. When we measure angles between two vectors, we measure the angle between two vectors, we need to shift their tails together. We need to shift their tails together. For example, suppose I have one vector looks like this. That's vector A. Vector B looks like this. How do we measure the angle between vector A and B? This is not angle between vector A and B. Be very careful. This is not angle between A and B. In order to measure the angle between vectors A and B, we must shift their tails together. So shift vector A here. Keep the same length and the same direction. Shift vector A here. We must shift their tail together. In order to measure angle between two vectors, we must shift their angle together, their tails together. This is angle theta. This vector is the sense vector A. This vector is the sense vector A. That's the angle between vectors A and B. Another example. We have vector A and B. In order to find the angle between these two vectors, this is not an angle between two vectors. We must shift their tail together, then measure the angle. In order to find the angle between two vectors, in order to measure the angle between two vectors, we must shift their tails together, then measure the angle. I can shift vector A here. Keep the same direction, but with the same length. Keep the same direction, and the length must be the same. This is also vector A. Then once I shift their tail together, I can measure the angle between two vectors. This is angle theta. So be very, very careful. When we measure the angle between two vectors, we must shift their tails together, then measure the angle. And another thing is, angle theta is always between 0 and 180. But what if an angle between two vectors is more than 180? What if an angle between two vectors is more than 180? then what should we do? Remember, for angle between two vectors, we take the smaller angle. For angle between two vectors, we take smaller angle. This is angle theta. Angle theta is always between 0 and 180. It won't be more than 180. For angles between two vectors, we take a smaller angle. So theta is always between 0 and pi. Next, let's try a simple example. Let vector A be 1, 2, 3. Vector B be -2, -1, and 1. And let vector C be -3, 0, 1. Find the angle between vector A and B and the angle between vector A and C. Let's first of all find angle between vectors A and B first. So using the formula, cosine theta equal to dot product of vector A dot B divided by the magnitude of vector A times magnitude of vector B. Let's compute the dot product first. Dot product A dot B, we multiply the corresponding component, add them up. 1 times -2 is -2. 2 times -1 is -2. 3 times 1 is 3. So the dot product is -1. Now the denominator, let's compute the magnitude for vector A and B. For vector A, the magnitude is square root of 1 squared plus 2 squared plus 3 squared. 1 squared is 1, 2 squared is 4, 3 squared is 9, 1 plus 4 plus 9 is 14. Then for magnitude of vector B, we have -2 squared, which is 4, -1 squared is 1, 1 squared is 1, 4 plus 1 plus 1 is 6, and then multiply. Radical 14 times radical 6 is radical 84. Then how do we find angle theta here? How do we find angle theta here? We know that for inverse cosine, for the function of inverse cosine, its range is from 0 to pi. For the function of inverse cosine, its range is from 0 to pi. And also we know that theta is the angle between two vectors. Theta is also between 0 and pi. Since the range of inverse cosine function is between 0 and pi, angle theta is also between 0 and pi. So we can apply inverse cosine function. We can apply the function of inverse cosine directly to find angle theta. Since the range of inverse cosine is between 0 and pi, and we know that theta is also between 0 and pi, so in order to find angle theta, we can apply inverse cosine directly to find angle theta. So keep this in mind. So for angle theta here, we can apply inverse cosine directly. Inverse cosine of -1 over radical 84. Apply inverse cosine function directly for angle theta. And I use my calculator, I get 96.26 degrees in my calculator. That's the angle between vectors A and B. Now for angle between vectors A and C, use the same formula. cosine theta between vector A and C, we first of all compute the dot product of AC, then divide by magnitude of vector A times magnitude of vector C. Now A dot C, let's compute dot product first. We multiply the corresponding component and then add them up. 1 plus negative 3 is negative 3. Sorry, 1 times negative 3 is negative 3. 2 times 0 is 0. 3 times 1 is 3. Adding up, I get 0 on the numerator. On the denominator, magnitude of vector A. 1 squared is 1, 2 squared is 4, 3 squared is 9. 1 plus 4 plus 9 is 14. And then magnitude of vector C. Negative 3 squared is 9, 0 squared is 0, 1 squared is 1, 9 plus 0 plus 1 is 10. So denominator is square root of 140. 0 over square root of 140 is 0. Then to find angle theta, we apply inverse cosine of 0. Inverse cosine of 0 is 90 degrees. You know the cosine pi over 2 is 0. Cosine pi over 2 is 0. So angle theta must be 90 degrees. That's the angle between vector A and C. Note, if the dot product between two vectors is 0, if the dot product between two vectors is 0, then since cosine theta is always A dot B divided by their magnitude, if the dot product is 0, then the entire expression here is 0. If the numerator is 0, then the entire expression is 0. Then cosine theta will be 0. If cosine theta is 0, then theta must be 90 degrees. Which means vector A and B, they are perpendicular. So based on this relationship here, we define perpendicular vectors in the following way. Perpendicular vectors, sometimes it's also called orthogonal vectors. It means the same thing. Perpendicular vector is also sometimes called orthogonal vectors. It means the same thing. Perpendicular means orthogonal. Orthogonal means perpendicular. So let A and B be two vectors in R3. If the dot product of AB is 0, if the dot product of AB is 0, then we say A and B are perpendicular vectors. Or orthogonal. We say A and B are perpendicular or orthogonal. So that's how we define perpendicular vector. If the dot product of two vectors is 0, then two vectors perpendicular. How about parallel vectors? We define parallel vectors in a very, very similar way. Let A and B be two vectors in R3. If vector A equal to k times b, where k is a real number, then we say vectors A and B are parallel. if A equal to k times b, that means A is a constant multiple of vector b. If A is a constant multiple of vector b, then we say vectors A and b are parallel. Now, how does this definition make sense? Let's verify this definition with this formula, and we'll see how it makes sense. Let A equal to kb. Let vector A equal to k times vector b. Where k is a real number. And let theta be the angle between vectors A and b. According to the previous theorem, cosine theta equal to vector A dot b over magnitude of vector A times magnitude of vector b. Now plug in. Since vector A equal to k times b, I have k times b dot b. I have k times vector b dot b on the numerator. On the denominator, I have magnitude of kb times magnitude of vector b. Then, by one of the property about dot product, I can pull k out. If I pull out k, I have k times b dot b. Since k is a scalar, I can pull out k. That's the numerator. On the denominator, I can also pull out k. Since this is the magnitude of a vector, when I pull out k, it's absolute value of k times magnitude of vector b times magnitude of vector b. Since this is the magnitude, when I pull k out, I need to add absolute value for number k. Then, on the numerator, k times dot product of vector b dot b by the first property of dot product. B dot b is magnitude of vector b squared. And on the denominator, we have absolute value of k times magnitude of b times magnitude of b, which is magnitude of vector b squared. Cancel magnitude of b from top and bottom. What's left is k over absolute value of k, which is either positive 1 or negative 1. Since cosine theta is positive or negative 1, since cosine theta is either positive or negative 1, we know that when cosine theta is 1, theta is 0 degree. And if cosine theta is negative 1, then theta is 180 degree. We know that cosine 0 is 1, cosine pi is negative 1. So if cosine theta is 1, theta must be 0 degree. If cosine theta is negative 1, theta must be 180 degree. If the angle between two vectors is 0 degree, that means two vectors must be parallel vectors. if the angle between two vectors is 0 degree, that means two vectors must lie on the same line. If the angle between two vectors is 0 degree, they must lie on the same line and point in the same direction. If the angle between two vectors is 180 degree, if the angle between two vectors is 180 degree, that means they lie on the same line, but they point in the opposite direction. If an angle between two vectors is 0 degree, then they lie on the same line and point in the same direction. These two vectors lie on the same line and point in the same direction. If the angle between two vectors is 180 degree, then these two vectors lie on the same line, but they point in the opposite direction. In both cases, these two vectors are parallel vectors. In both cases, these two vectors are parallel vectors. So that's how this definition makes sense. So, if the dot product of two vectors is 0, then two vectors are perpendicular. And if one vector is a constant multiple of another vector, then two vectors are parallel. That's the definition for perpendicular and parallel vectors. Note, according to this definition, 0 vector is perpendicular and parallel to every other vectors. Zero vector is perpendicular and parallel to every vector. Because dot product 0 dot any vector is 0. Because dot product 0 dot any vector is 0. And 0 vector can always be written as 0 times every vector. So 0 vector is a constant multiple of every vector. 0 vector dot product 0 dot every vector is 0. For dot product 0 vector dot every vector is 0. And 0 vector can always be written as 0 times another vector. That means 0 vector is a constant multiple of every vector. So 0 vector is perpendicular to every vector and parallel to every vector. Now let's do a simple example about perpendicular and parallel vectors. Let vector A equal to 1, 4, negative 2. Vector B equal to 4, negative 3, negative 4. And vector C equal to negative 2, negative A, and 4. Part A. Determine whether vectors A and B are parallel, perpendicular, or neither. Determine whether vector A and B are parallel, perpendicular, or neither. Let's check parallel first. For vector A and B, if I divide a component, what do I get? If I divide a component, vector A, the component is 1, 4, negative 2. For vector B, the component is 4, negative 3, negative 4. If I divide a component, 1 divided by 4, the ratio is 1 over 4. 4 divided by negative 3, the ratio is negative 4 over 3. Negative 2 divided by negative 4, the ratio is 1 over 2. Since the ratio between every component is different, then we know that A and B are not parallel. It means I cannot write A as a constant multiple of B. So A and B, they are not parallel. Since the ratio of every component is different, That means we cannot write A as a constant multiple of B. Then A and B, they are not parallel to each other. Since the ratio between every component is different, vectors A and B, they are not parallel. How about perpendicular? Let's check their dot product. A dot B. Multiply the corresponding component and add them up. 1 times 4 is 4. 4 times -3 is -12. -2 times -4 is positive A. 4 minus 12 is -A. -A plus A is 0. Since the dot product of two vectors is 0, then we know A and B are perpendicular. So vector A and B are perpendicular. Next, determine whether vectors A and C are perpendicular, parallel, perpendicular, or neither. Determine whether vectors A and C are parallel, perpendicular, or neither. Now for vector A and C, let's check if they are parallel. Vector A is 1, 4, -2. Vector B is, vector C is -2, -A, and 4. Let's check their ratio. Divide each component and check the ratios. 1 divided by -2 is -1/2. 4 divided by -A is also -1/2. -2 divided by 4 is also -1/2. Since the ratios between every component is the same, that means vector A equal to -1/2 times vector C. If the ratios is -1/2 for every component, if the ratios is -1/2, that means vector A equal to -1/2 times vector C. So, since vector A is a constant multiple of vector C, then we know they are parallel. So vector A is parallel to vector C. How about perpendicular? Let's check dot product. A dot C, let's check dot product. Multiply the corresponding component and add them up. 1 times -2 is -2. 4 times -A is -32. -2 times 4 is -A. Add them up, we get -42, which is not 0. So vector A and C are not perpendicular. Vector A and C, they are not perpendicular. The answer is vector A is parallel to C. That's an answer. Vector A is parallel to vector C. Next, let's look at a theorem called triangle inequality. For any vectors A and B in R3, magnitude of vector A plus B is always less than or equal to magnitude of vector A plus magnitude of vector B. This theorem has a name. It's called triangle inequality. Why is this called triangle inequality? Let me show you a picture. So, suppose this is vector A. If I try to do A plus B, I shift the tail of vector B to the head of vector A. If I try to do addition for two vectors, A plus B, I shift the tail of vector B to the head of vector A. That's vector B. Then connect the initial tail and the final head. This is vector A plus B. This picture is a triangle. this picture is a triangle, and we know that this side, the length of this side, is shorter than the length of these two sides. The length of this side, magnitude of vector AB, is less than magnitude of A plus magnitude of B. The length of this side is less than the length of these two sides. So magnitude of vector A plus B is less than magnitude of vector A plus magnitude of vector B. That's why this formula is called triangle inequality. Now let's prove it. Let me start from the left side. I try to show left side is less than the right side. Magnitude of vector A plus vector B. Let me first of all square the magnitude. Then I'll take square root at the end. Let me first of all square this magnitude. Then, by the first property of dot product, I treat A plus B as one vector. I can write this as vector A plus B dot vector A plus B. Then apply distribute property. Apply distribute property. I have vector A dot A plus vector A dot B plus vector B dot A plus vector B dot B. We know that vector A dot A is the magnitude of vector A squared. And the dot product A dot B is the same as the dot product B dot A. Then I can combine like terms like this, twice vector A dot B. And vector B dot B is the magnitude of vector B squared. Now, by a theorem we learned earlier today, we know that dot product A dot B can be rewritten as magnitude of vector A times magnitude of vector B times cosine theta, where theta is the angle between vectors A and B. Theta is the angle between A and B. Now, we know cosine theta. Cosine theta is always varies between -1 and 1. Cosine theta is always between -1 and 1. So we can say that cosine theta is less than 1. So cosine theta is less than 1 for all theta. So cosine theta is less than or equal to 1 for all theta. Therefore, this expression, if I replace cosine theta with 1, I get a larger expression. So, magnitude of A squared stays the same. Magnitude of B squared stays the same. 2AB stays the same here. If I change cosine theta to 1, I make the new expression larger than the old expression. This expression is larger than the old expression. This is larger than this. So this is equal to magnitude of vector A squared plus twice magnitude of vector A times magnitude of vector B plus magnitude of vector B squared. And this is a perfect square. This is a perfect square. A squared plus 2AB plus B squared. This is a perfect square. This can be rewritten as magnitude of vector A plus magnitude of vector b square. This is a perfect square, so I can write it as magnitude of vector A plus magnitude of vector b square. So we have magnitude of A plus magnitude of vector A plus b square is less than or equal to, this is less than this, less than or equal to magnitude of vector A plus magnitude of vector b square. Since they are both positive, magnitude of vector A plus b is positive number. Magnitude of A is positive. Magnitude of vector b is also positive. Positive number plus positive number is positive. Since they are both non-negative, they are both positive, I can take square root on both sides. If I take square root on both sides, I have magnitude of A plus b is less than or equal to magnitude of vector A plus magnitude of vector b. That's a proof of the triangle inequality. Next, we will study the cross product. Before I show you what is the cross product, let me first introduce the determinant first. Determinant of order 2. Suppose we have a 2 by 2 matrix A, B, C, D, and this 2 bar here represent the determinant of this matrix. The determinant of a 2 by 2 matrix is defined as AD minus BC. The determinant of a 2 by 2 matrix is defined as AD minus BC. What does it mean? Its geometry meaning is we treat AB as a vector, treat the first row AB as a vector. Treat the second row CD as another vector. The determinant is absolute value. The absolute value of the determinant represents the area of the parallelogram determined by these two vectors. So the absolute value of the determinant represents the area of the parallelogram determined by the vectors AB and CD. So the absolute value of the determinant A, B, C, D represent the area of the parallelogram determined by vectors AB and CD. So this determinant is a value. This value, its absolute value, represents the area of the parallelogram determined by these two vectors AB and CD. So that's determinant of order 2. And here, let me show you an example. Suppose we have a 2 by 2 matrix, 1, 2, 3, 0. And we take the determinant. We have AD minus BC, 0 minus 6, which is negative 6. That's the determinant of this 2 by 2 matrix. Its absolute value, if I take an absolute value, its absolute value represents the area of the parallelogram determined by vectors 1, 2, 3, 0. Let me show you a picture. Suppose vector 1, 2 is here. This is vector 1, 2 in the xy plane. Vector 3, 0, 1, 2, 3. Vector 3, 0 is here. Suppose next vector 3, 0. For two vector, we can determine a parallelogram. I shift this side here. Shift this vector here. And shift this vector here. It forms a parallelogram. This is the parallelogram determined by vectors 1, 2, and 3, 0. The absolute value of the determinant, positive 6, represents the area of this parallelogram. Can we verify the area? We know that area of a parallelogram is always the base area times the height. So it's always the base times height. Area of parallelogram is always the base times height. What's the base here? Base here is 1, 2, 3. So the base of the parallelogram is 3. What's the height of the parallelogram? The height. That's the height of the parallelogram. This height is 2. The height of the parallelogram is 2. So the area, base times height, 3 times 2 is 6. So the area of this parallelogram is 6. If I take an absolute value from the determinant, I also get positive 6. So the absolute value of the determinant represents the area of the parallelogram determined by these two vectors. Next, let me show you determinant of order 3. Determinant of order 3 looks like this. Suppose we have a 3 by 3 matrix. A, B, C, D, E, F, G, H, I. Suppose we have a 3 by 3 matrix. A 2 bar represent the determinant of this matrix. 2 bars here represent the determinant of this matrix. For determinant of this matrix, there are many ways to find determinant. Let me show you one way here. To find determinant of a 3 by 3 matrix, one of the techniques is called Cofactor Expansion. To find determinant of a 3 by 3 matrix, one of the techniques is called the Cofactor Expansion. So let me show you the Cofactor Expansion. So choose the first row. I choose the first row. The first element in the first row is A. I write A here. Cross out first row. Cross out the row and the column that contains A. What's left is a 2 by 2 matrix, E, F, H, I. In the first row, the second number is B. The sign is always plus, minus, plus. So write minus B. Positive A minus B. The next one is plus C. Minus B. B is here. If I cross out the row that contains B and the column that contains B, what's left is DF, is DG, FI. And this 4 number form a matrix, DFGI. If I cross out the row and the column that contains B, what's left is DGFI. And this 4 number form a matrix, DFGI. Then in the first row, the last number is C, plus C. The sign is always plus, minus, plus, plus, minus, plus. So I cross out a row and a column that contains C. If I cross out a row and a column that contains C, what's left is DEGH. DEGH. Next, we can compute the determinant of each 2 by 2 matrix. After we find the determinant for each 2 by 2 matrix, we can multiply and add them up. We get a value. This value represents the determinant of this 3 by 3 matrix. And this expression is called the Cofactor Expansion of this 3 by 3 matrix. This expression is called a Cofactor Expansion. So that's a cofactor expansion of this 3 by 3 matrix. Using cofactor expansion, we can always find the determinant of a 3 by 3 matrix. Next, let me show you what does the determinant of a 3 by 3 matrix means. Let me show its geometry meaning. We first of all consider each row as a vector. We consider ABC as a vector, DEF as another vector, GHI as another vector. Assume that's vector ABC. Assume that's vector DEF. Assume this is vector GHI. The determinant of this 3 by 3 matrix, its absolute value represents the volume of a parallel P determined by these 3 vectors. How is a parallel P determined by these 3 vectors looks like? Let me show you the picture. This is a parallel P determined by these 3 vectors, ABC, DEF, and GHI. The absolute value of this 3 by 3 matrix represents the volume of the parallel P determined by the vectors ABC, DEF, and GHI. The absolute value of this determinant A, B, C, D, E, F, GHI represent the volume of the parallel P determined by vectors A, B, C, D, E, F, and GHI. So the absolute value of this determinant represents the volume of the parallel P determined by vectors A, B, C, D, E, F, GHI. If we treat each row as a vector, 3 vectors determine a parallel P, and the absolute value of the determinant represents the volume of this parallel P. That's its geometry meaning. Next, let me show you some example about determinants. Find the determinant for each of the following matrices. First one, consider matrix 1, 3, 2, -3, -1, -3, 2, 3, 1. Find the determinant for this matrix. So here we can use cofactor expansion for a 3 by 3 matrix. If we want to find the determinant, we can apply cofactor expansion. So we choose the first row. First coefficient is 1. Cross out first row, first column. What's left is a 2 by 2 matrix. -3, -1, -3, 3, 1. Second number is number 3. Cross out first row, second column. And sign here is plus, minus, plus. For second number, the sign is minus. Cross out first row, second column. We have -3, 2, -3, 1. These four numbers form a 2 by 2 matrix. The third number is number 2. If I cross out first row, third column, what's left is a 2 by 2 matrix here. -3, -1, 2, 3. Then compute each 2 by 2 matrix. Compute each 2 by 2 matrix. For 2 by 2 matrix, we can compute AD minus BC. So I get -1 minus -9. -1 minus -9. For this 2 by 2 matrix, we have AD minus BC, -3 minus -6. For this 2 by 2 matrix, we have -9 minus -2. Then compute the determinant here. We have A 3 and -7. Adding up, we have A minus 9 minus 14. Together is -15. This is the determinant of this 3 by 3 matrix. -15 represents the determinant of this 3 by 3 matrix. Its geometry meaning is its absolute value. If I take absolute value, this number represents the volume of a parallel pi p determined by vectors 1, 2, 3, -3, -1, -3, 2, 3, 1. If I take absolute value for -15, I get positive 15. Positive 15 represents the volume of the geometry pi p determined by these 3 vectors. Next example, find the determinant of a 3 by 3 matrix. 2, -3, 1, 2, 0, -1, 1, 4, and 5. So for 3 by 3 matrix, if we want to compute the determinant, use Cofactor Expansion. In the first row, first number is number 2. If I cross out first row, first column, what's left? It's a 2 by 2 matrix. 0, -1, 4, 5. The second number is -3. Now be very, very careful here. The sign for each number here is positive, negative, positive. So first number is positive. Second number, add negative sign. -3. For second number, add negative sign. We have -3. If I cross out the first row, second column, what's left is 0, 1, -1, 5. These four numbers form a 2 by 2 matrix. 2, -1, 1, 5. The third number in the first row is number 1. The sign is positive. Then cross out first row, third column, we have a 2 by 2 matrix here. 2, 0, 1, 4. Then compute the determinant for each 2 by 2 matrix. 0 times 4 is 0. Minus 4 times -1 is -4. Minus -4 is +4. Next, double negative is positive. We get +3 here. Then find determinant. 2 times 4 is 10. 1 times -1 is -1. 10 minus -1 is 10 plus 1. Next, we have 1 times determinant of this matrix. 2 times 4 is 8. 1 times 0 is 0. Then we have 2 times 4 plus 3 times 11 plus 1 times 8. That's A plus 33 plus A, which is 49. So 49 is the determinant of this 3 by 3 matrix. Now we know the determinant. Next, let me introduce the cross product. Let A equal to A1, A2, A3, and B equal to B1, B2, B3, be vectors in R3. The cross product of A and B is defined as A cross B A cross B equal to the determinant of the matrix I, J, K in the first row. I, J, K are the standard basis, where I is 1, 0, 0. J is 0, 1, 0. K is 0, 0, 1. I, J, K, they are standard basis in R3. So in the first row, write vectors I, J, K. In the second row, write the components of vector A. In the second row, write the components of vector A, which is A1, A2, A3. In the third row, write the components of vector B, which is B1, B2, B3. Then compute the determinant, we get a cross product. If we compute the determinant here, we use Cofactor Expansion. We have I times cross our first row, first column. We have I times matrix A2, A3, B2, B3. I times the determinant of this 2 by 2 matrix. Then the sign here is plus, minus, plus. Minus vector J times the determinant of the 2 by 2 matrix. And cross out first row, second column. We have these 4 numbers. These 4 numbers form a 2 by 2 matrix, which is A1, A3, B1, B3, plus K times the determinant of the matrix A1, A2, B1, B2. That's the definition of cross product. Next, let me show you an example. Let vector A equal to 2, 1, negative 1. Vector B equal to negative 3, 4, 1. Let vector C be the cross product of A cross B. And vector D be the cross product B cross A. So let vector A, let A be the vector 2, 1, negative 1. Let B be the vector negative 3, 4, 1. Let C be the vector. Let vector C equal to the cross product A cross B. Let vector D be the cross product B cross A. Find vector C. Vector D. The dot product of AC and the dot product of BC So let's find vector C first. Vector C is a cross product of A, B. Vector C is a cross product of A cross B. So by definition, we first of all put vector I in the first row, vector J, vector K, put a standard base ijk in the first row. Then write a component of vector A in the second row. Write a component of vector B in the third row. Then find the determinant using Cofactor Expansion. Find the determinant using Cofactor Expansion. First row ijk. First number in the first row is I. Cross our first row, first column, I have 1, -1, 4, 1. Second number is J. Write -J times. I cross our first row, second column. I have 2, -1, -3, 1. Plus K times. For K, I cross our first row, third column. I have 2, 1, -3, -3, and 4. Then compute determinant for each 2x2 matrix. If I compute determinant for the first matrix, I have 1 minus 4, 1 minus -4. For the second matrix, I have 2 minus 3. For the third matrix, I have A minus -3. That's 5i plus 1j plus 11k. So if I write this in vector form, I can write it as a vector 5, 1, 11. This is vector C. This is vector C. That's a cross product of A cross B, which is vector C. Next, let's compute vector D. Vector D is a cross product B cross A. So by definition of cross product, I first of all put a standard base I, J, K in the first row. In the second row, since B comes first, I run a component of vector B in the second row here. Since B comes first, I run a component of vector B in the second row. I get -3, 4, 1. Then I write a component of vector A in the third row. I get 2, 1, -1. Then use Cofactor Expansion for the determinant. I have I times the determinant of the matrix 4, 1, 1, -1. Minus J times determinant of the matrix -3, 1, 2, -1. Plus K times determinant of the matrix -3, 4, 2, 1. Then compute the determinant for each 2x2 matrix. I have -4 minus 1, 3 minus 2, -3 minus 8. Then we have -5i minus 1j minus 11k. If I write it in vector form, that's a vector -5, -1, and -11. So vector D is -5, -1, -11. Next, let's compute the dot product A dot C. Vector A is the vector 2, 1, -1. Vector C is the vector 5, 1, 11. If I do the dot product, I multiply the corresponding components, then add them up. 2 times 4 is 10. 1 times 1 is 1. Negative 1 times 11 is negative 11. Adding up, I get 0. If the dot product is 0, that means vector AC are perpendicular. So here we can say that vector AC are perpendicular since their dot product is 0. Vector AC are perpendicular since their dot product is 0. Now how about dot product of vector ABC? Vector B is the vector negative 3, 4, and 1. Dot vector C. Vector C is 5, 1, 11. Then for dot product, we multiply the corresponding entries and adding up. Negative 3 times 5 is negative 15. 4 times 1 is 4. 1 times 11 is 11. Adding up, I get 0. Since I get 0 again, if the dot product of vector BC is 0, that means vector B and C are perpendicular. So here you can see that vector C is the cross product of A and B, and C is perpendicular to both vectors A and B. So for cross product, keep this idea in mind. The cross product of any two vectors, generates a new vector which is perpendicular to both vectors. Like here, we have C equal to the cross product of A, B. When we do cross product A cross B, it generates a new vector C. This vector C is perpendicular to both vector A and B. So the cross product of AB generates a new vector C, and this new vector C is perpendicular to both vectors A and B. So keep this rule in mind. Cross product of two vectors always generates a new vector which is perpendicular to both vectors. And you can verify this rule by doing the following computation. Let A be the vector A1, A2, A3. Let B be the vector B1, B2, B3, and C equal to vector A cross B. You can first of all compute the cross product A cross B, then get a new vector C. Then you can do the computation. Show that the dot product of A dot C is 0, and the dot product of B dot C is 0. You can verify this rule by yourself. First of all, compute vector C, then do dot product A dot C and B dot C. If you calculate everything correctly, you should get 0 for both vectors. That means the cross product generates a new vector that's perpendicular to both vectors. Here we know that when we compute cross product for two vectors, it generates a vector that's perpendicular to both vector A and B. Let me show a picture. Suppose that's vector A, that's vector B. The cross product A cross B, it generates a vector that's perpendicular to both A and B. this vector, it may go up or it may go down. How do we determine the direction? This vector A cross B, it generates a vector that's perpendicular to both vector A and B. This vector, it may go up, it may go down. How do we determine the direction? Here, let me introduce a screwdriver rule. A screwdriver rule. When we do cross product A cross B, consider we have a screwdriver. We turn from A to B. Consider we have a screwdriver. We turn from A to B. We turn in this direction. If we turn a screwdriver in this direction, clockwise, if we turn a screwdriver clockwise, we are pulling the screw out. If we turn a screwdriver clockwise, we are pulling the screw out. So the cross product is a vector that's pointing upward. When we turn screwdriver clockwise, we are pulling the screw out. So the cross product generates a vector that points upward. On the other hand, if I compute B cross A, for the same vectors, if I compute B cross A, for the same vectors, if I compute the cross product B cross A, I turn the screwdriver this way. If I compute cross product B cross A, I turn the screwdriver counterclockwise. If we turn the screwdriver counterclockwise, we are putting the screw in. When we turn in the screwdriver counterclockwise, we are putting the screw in. So the cross product B cross A generates a vector that points downward. When we apply cross product B cross A, we turn the screwdriver from B to A. We turn the screwdriver counterclockwise. When we turn the screwdriver counterclockwise, we are pulling the screw in. We are putting the screw in. So the cross product B cross A generates a vector that points downward. When we turn the screwdriver from A to B, we turn the screwdriver clockwise. That means we are pulling the screw out. So it generates a vector points upward. When we turn the screwdriver from B to A, I turn the screwdriver counterclockwise. When we are turning screwdriver counterclockwise, we are putting the screw in. So the cross product B cross A generates a vector that points downward. So that's how we use screwdriver rule to determine the direction of cross product geometrically. That's vector B cross A. And in general, we can see that here. The cross product of A cross B and B cross A, they always point to an opposite direction. So cross product of A cross B and B cross A, they are always point to an opposite direction. They are parallel vectors, but they always point to an opposite direction. A cross B, B cross A, they always point to an opposite direction. They are parallel vectors, but they always point to an opposite direction. Next, let me show you some properties about cross product. Let A, B, C be vectors in R3. Let A, B, C be vectors in R3. And let a real number K be a scalar. Let a real number K be a scalar. First property, cross product A cross B is always the same as negative B cross A. We know that cross product A cross B always generates a vector that's perpendicular to both vector A and B. But if I switch order, B cross and do B cross A, I get a vector that also perpendicular to both vectors A and B, but it points in the opposite direction of vector A cross B. I still get a vector that's perpendicular to both vectors A and B, but it points in the opposite direction. That's first property. If I switch order of cross product, I change the sign of the cross product. Next, vector A cross B plus C is the same as A cross B plus A cross C. That's called distributive property. I can distribute A to both B and C. Next, K times cross product A cross B. If there's a K times the cross product A cross B, I can either put K together with vector A, like KA cross B, or I can put K together with vector B, like A cross KB. So if there's a K multiplied by a cross product, I can either put K together with vector A, or I can put K together with vector B. Next, A dot B cross C equal to vector A cross B dot C. On the left side, we do cross product for vector B and C first, then dot it with vector A. And on the right side, we do cross product for A cross B first, then dot it with vector C. Sometimes, in some problem, doing cross product for A cross B is easier than cross product B cross C. So using this formula, we can change the order of operations. Sometimes it can make the problem easier. Next, A cross B cross C. This is the same as vector A dot C times vector B minus vector A dot B times vector C. When we do dot product A dot C, the answer is a real number. We can consider this is a scalar. We have a scalar times a vector minus a scalar times a vector. So on the left side here, we have cross product twice. We have to do cross product twice. Sometimes it's not easy. Doing cross product twice is not easy. On the left side, on the right side, according to this formula, I can change double cross product into double dot products. We have dot product twice. Doing dot product in general is much easier than doing cross product. So using this formula, we can simplify the calculation. In general, doing dot product is much easier than doing cross product twice. Doing dot product twice is much easier than doing cross product twice. So use this formula, we can simplify the calculation. Those are the properties about cross product. We can verify each formula. By letting vector A equal to vector A1, A2, A3. Vector B equal to B1, B2, B3. Vector C equal to C1, C2, C3. We can let vector A, B, C be these vectors. Then plug in each vector here and show that left side on each formula show that left side equal to the right side. That's how we verify the formula. You can verify this by yourself. Plug in vector A, B, C and verify that left side equal to the right side. Next, let's look at a theorem about cross product. Let vectors A and B, let A and B be vectors in R3, and let theta be the angle between vectors A and B. Then the magnitude of vector A cross B is the same as the magnitude of vector A times the magnitude of vector B times sine theta. Magnitude of vector A cross B is the same as magnitude of vector A times magnitude of vector B times sine theta, where theta is an angle between vectors A and B. Let's prove it. So when we try to prove this theorem, we try to prove left side equal to the right side. Left side is the cross product A cross B. Magnitude of the cross product A cross B. I try to prove this equal to the right side. Let me first of all square left side first. And in the end, I'll take square root. Let me square left side first. If I square left side, I have magnitude of A cross B squared. And by the first property of cross product, of dot product, the first property of dot product says for any vector A dot A, that's always the same as magnitude of vector A squared. That's the first property of dot product. So here, A cross B, I can treat this as one vector. So I apply this property. I can write magnitude of a vector square as the vector dot itself. So I can write magnitude of a vector square as the vector dot itself. I treat A cross B as a vector. So I have a vector dot itself. Next, we try to rewrite this formula. The fourth property of cross product. The fourth property of the cross product says for any vector A dot B cross C, that's the same as the cross product A cross B dot C. That's the fourth property of the cross product. We try to use it here. I treat this as vector A, treat this as vector B, treat this as vector C. Let me write this formula in a different way. It'll be a little easier. Let me write U dot V cross W. It'll be a little easier. U cross V dot W. So U dot V cross W is the same as U cross V dot W. So I treat my first vector, this as U, this as B, this as V, treat this as W. So I have U cross V dot W, that's U, that's V, that's W. I have U cross V, that's my vector U, cross V, dot W. I treat this as my vector U, that's my vector V, that's my vector W. Plug into the right side, I have U cross V dot W. That's the fourth property of the cross product. Then I try to use the fifth property of the cross product. The fifth property of cross product says A cross B cross C can be rewrite as A dot C first dot last times the middle minus A dot B first dot the second times the last. That's the fifth property of cross product. A cross B cross C is the same as first dot the last times the middle minus first dot the second times the last. That's the fifth property of cross product. Now, what we have here is A cross B cross A. In order to match this format, I need to switch the order for these two terms. So if I switch order of cross product by the first property of cross product, if I switch order of cross product, I need to add negative sign in the front. So this is the same as vector A cross B dot B. If I switch order for cross product, I need to add negative sign in the front. That's the first property of cross product. A dot A cross B is the same as negative B cross A. If I switch order for cross product, I add negative sign in the front. If I switch order for this cross product, I add negative sign in the front. Then this formula is in the form of A cross B cross C. This formula is in the form of A cross B cross C. And this formula here says this double cross product equal to the first dot the last times the middle minus the first dot the second times the last. So use the formula here. I have the first dot the last times the middle minus the first dot the second times the last, and this b stays the same. So this part, I use this formula here. First dot the last times the middle minus the first dot the second times the last. That's this formula. First dot the last times the middle minus first dot the second times the last. So I will write this double cross product as two dot products. Now next, if I distribute negative sign, it can be rewritten as A dot A times B minus A dot B times A dot B. If I distribute negative sign, the second term becomes positive, first term becomes negative. Then I can distribute vector B. That's the distribute property of dot product. Vector A plus B dot C. If I apply distribute property for dot product, I can write it as vector A dot C plus vector B dot C. That's the distribute property for dot products. So distribute vector B. Remember, this is a scalar. Don't touch the scalar. This is scalar. Only distribute a vector to the vector. This is a scalar. Don't touch the scalar. So after distribute, we have A dot A times vector B dot B. Distribute B to B. This is a scalar. This is a number. Don't touch it. Vector B dot B minus vector A dot B times vector A dot B. So distribute vector to the vector. This can be rewritten as vector A dot A times vector B dot B minus vector A dot B times vector A dot B. That's a property of dot product. Says Ka dot B is the same as K times A dot B. That's a property of dot product. If there's a scalar multiplied to a vector dot another vector, I can write a scalar in the form so after I distribute, that's one vector dot vector B. That's another vector dot vector B. This is a scalar. A dot A is a scalar. I can put it in the form. If I write A dot A in the form, I have B dot B. If I write A dot B in the form, I have A dot B here. Then by the first property of dot product, A dot A is magnitude of vector A square, and vector B dot B is magnitude of vector B square. A dot B times A dot B, that's vector A dot B square. A dot B times A dot B, that's A dot B square. And we know that by the theorem, in the previous section. But the theorem in the previous section, for any vector A dot B, that can be rewritten as magnitude of vector A times magnitude of vector B times cosine theta. Vector A dot B, dot product A dot B is always the same as the magnitude of vector A times magnitude of vector B times cosine theta. So plugging here, we have magnitude of vector A times magnitude of vector B times cosine theta square. Then distribute square. I have magnitude of vector A square times magnitude of B square minus magnitude of vector A square times magnitude of vector B square times cosine square theta. Now you can see that here, magnitude of vector A and B, they are common factors. If I pull out a common factor, I have magnitude of vector A square times magnitude of vector B square times 1 minus cosine square theta. If I pull out the common factor, magnitude of vector A square, magnitude of vector B square, what's left is 1 minus cosine square theta. And by the trig identity, we know that 1 minus cosine square theta is sine square theta. So I get magnitude of vector A square times magnitude of vector B square times sine square theta. So we have, so here we have cross product of A cross B. The magnitude of the cross product A cross B square equal to magnitude of vector A square times magnitude of vector B square times sine square theta. If I take square root on both sides, I have magnitude of vector A cross B on the left side, because the magnitude is always positive. When I take square root cancels square. And when I take square root on the right side, square root of magnitude of vector A square is magnitude of vector A. Because magnitude of vector A is always positive, so square root cancels square. And for magnitude of vector B, same thing. Since this is always positive, square root cancels square, so I get magnitude of vector B by itself. Now for sine function, this angle theta is angle between two vectors. This theta is angle between two vectors. So theta must be between 0 and 180. Since theta is between 0 and pi, that means theta lies in the quadrant 1 and quadrant 2. Sine function is positive in both quadrant 1 and quadrant 2. Since theta is between 0 and pi, means theta is between quadrant 1 and quadrant 2. Theta lies in quadrant 1 and quadrant 2. In quadrant 1 and quadrant 2, sine function is always positive. In quadrant 1 and quadrant 2, sine function is always positive. Since sine function is always positive, when I take square root, square cancels square root. I get sine theta here. Then, that's a proof of this theorem. Magnitude of vector A cross B is the same as magnitude of vector A dot magnitude of vector B times sine theta. Note, the previous formula sometimes can be written as sine theta equal to the magnitude of A cross B over the magnitude of vector A times the magnitude of vector B. especially when we're doing calculation. When we're doing calculation, sometimes using this formula is easier than the original formula. Next, let's look at a simpler theorem. Let A and B be vectors in R3. If vectors A and B are parallel, then the cross product A cross B must be the zero vector. Let's prove it. First of all, let theta be the angle between vectors A and B. Since A and B are parallel, then angle theta is either 0 or 180. Since vectors A and B are parallel, the angle theta is either 0 or 180. If vector A and B, they are parallel and point in the same direction, then the angle between two vectors is 0 degree. But if they are parallel, if vectors A and B they are parallel but point in the opposite direction, the angle between two vectors is 180 degree. There's only two possibilities. If when two vectors are parallel, either they are pointing in the same direction or they are pointing in the opposite direction. When they are pointing in the same direction, the angle between two vectors is 0. When they are pointing in the opposite direction, the angle between two vectors is 180 degree, which is pi. So since vector A and B are parallel, there's only two possibilities. Theta is either 0 or pi. In both cases, sine theta is 0. Sine of 0 is 0. Sine pi is also 0. In both cases, sine theta is 0. So, by the previous formula, by the previous theorem, magnitude of A cross B equal to magnitude of vector A dot times magnitude of vector B times sine theta. Since when theta equals 0 or pi, sine theta is always 0. When theta is 0 and pi, sine theta is always 0. Magnitude of A cross B equal to 0. When sine theta is 0. So magnitude of A cross B equal to 0 when sine theta is 0. If a vector has magnitude 0, this vector must be a 0 vector. If a vector has magnitude 0, this must be a 0 vector. Hence, since this vector has magnitude 0, this must be a 0 vector. Hence A cross B is a 0 vector. If the magnitude of a vector is 0, then this vector must be a 0 vector. Let's complete the proof. So, if two vectors are parallel, then their cross product is always 0. It's always a 0 vector. If two vectors are parallel, then their cross product is always a 0 vector. Next theorem. For any vectors A and B in R3, the magnitude of vectors A cross B always represent the area of the parallelogram determined by vectors A and B. So this theorem says the magnitude of vector A cross B always represent the area of the parallelogram determined by vectors A and B. how is the parallelogram determined by vector A and B looks like? Let me show you the picture first. Suppose that's vector A. Suppose that's vector B. Parallelogram determined by these two vectors looks like this. I first of all shift the tail of vector B. I first of all shift the tail of vector B to the head of vector A. I shift vector B to the head of vector A. Shift the tail of vector B to the head of vector A. Then I shift the tail of vector A to the head of vector B. I shift the tail of vector A to the head of vector B. These four sides, these four edges here, form a parallelogram. This parallelogram is called a parallelogram determined by vectors A and B. This parallelogram is the parallelogram determined by vectors A and B. And the theorem says the area of this parallelogram is the same as the magnitude of the cross product A cross B. How do we prove it? We know that the area of parallelogram is always base times height. Assume the height is h. Assume the height is h. The base is magnitude of vector B. And the height is h. Now, how do we find a simpler expression for h? Look at this triangle here. Let theta be the angle between vector A and B. So let h be the height of the parallelogram. Let me put the formula here. Let h be the height of the parallelogram. And let theta be the angle between vectors A and B. Then in this triangle here, we can consider h is the opposite side, and this side, vector A, as the adjacent side. I can consider h is the opposite side, and vector A as the hypotenuse. Consider h is the opposite, vector A as the hypotenuse. Then sine theta equal to opposite over hypotenuse, h over magnitude of vector A. Sine theta equal to opposite over hypotenuse. Hypotenuse is the length of vector A, which is the magnitude of vector A. So sine theta is h over magnitude of vector A. If I solve this equation for h, h equal to magnitude of vector A times sine theta. If I solve this equation for h equal to magnitude of vector A times sine theta. So area of the parallelogram equal to magnitude of vector B times h, which is magnitude of vector B times magnitude of vector A times sine theta. By the previous theorem, magnitude of vector A times magnitude of vector B times sine theta is magnitude of the vector A cross B by the previous theorem. They equal to magnitude of the cross product A cross B. That complete the proof. The area of the parallelogram is the same as the magnitude of the cross product A cross B. Next, let's look at a simple example. Let P equal to 2, 1, 1, Q equal to 0, 4, 1, and R equal to -2, 1, 4 be 3 points in R3. Find the area of triangle PQR. Let PQR be 3 points in R3. Find the area of the triangle PQR. What should we do here? So PQR, there are 3 points in R3. Assume that's point P, that's point Q, that's point R. If I join point PQ, I can find vector PQ here. If I join points P and Q, I can find vector PQ. If I join vectors PR, I can find vectors PR. Then we are looking for the area of this triangle PQR. We are looking for the area of this triangle PQR. And we know that if I shift this side, if I shift the vector PQ here, and shift the vector PR here, this is a parallelogram determined by vectors PQ and PR. If I shift vector PQ and shift vector PR here, sorry, if I shift vector PQ and shift vector PR, I have a parallelogram determined by vectors PQ and PR. By the previous theorem, we know that the area of the parallelogram determined by vectors PQ and PR is the magnitude of the cross product PQ cross PR. Then the area of this triangle is half of the parallelogram. The area of this triangle is half of the parallelogram. So we know that by the previous theorem, magnitude of the cross product PQ cross PR is the area of the parallelogram determined by vectors PQ and PR. And the area of the triangle is half of the parallelogram. The area of triangle PQR is half of this parallelogram. So we know that the area of triangle PQR is half of the magnitude of the cross product PQ cross PR. So let's compute the magnitude of the cross product PQ cross PR. Then times half. That's an area of triangle PQR. So let's first of all find vector PQ. For vector PQ, we use head minus tail, Q minus P. For vector PQ, use head minus tail, Q minus P. 0 minus 2 is negative 2. 4 minus 1 is 3. 1 minus 1 is 0. Vector PR, use head minus tail. Take point P minus point R, so point R minus point P. Head minus tail, point R minus point P. I get negative 4, 0, and 3. Then I find a cross product. PQ cross PR. Write I, J, K in the first column, in the first row. Write vector PQ in the second row. I get negative 2, 3, 0. Write vector PR in the third row. I have negative 4, 0, and 3. Then find a cofactor expansion for this 3 by 3 matrix. I have I times cross our first row, first column. I get 3, 0, 0, 3 minus J times the matrix. Negative 2, 0, negative 4, 3 plus K times the matrix. Negative 2, 3, negative 4, 0. Then find determinant. 3 times 3 is 9. 0 times 0 is 0. I got 9 minus 0. J times negative 6 minus 0 plus K times 0 minus negative 12, which is vector 9, 6, and 12. That's the cross product, PQ cross PR. Next, we find the magnitude of the cross product. Next, find the magnitude of the cross product. Which is square root of 9 square plus 6 square plus 12 square. Here I use my calculator. I get 3 radical 29. That's the area of the parallelogram. So from the area of the triangle, for area of triangle PQR, from the area of triangle PQR, I take half of the magnitude of cross product PQ cross PR. Take half of the magnitude of the cross product, which is 3 over 2 radical 29. That's the area of triangle PQ and R. Next theorem, let A, B, and C be vectors in R3. Then the volume of the parallel pipe determined by vectors A, B, and C is the absolute value of A dot B cross C. How do we prove it? Let's draw the picture first. Let's draw the parallel pipe determined by vectors A, B, and C first. Assume that's vector A. Assume that's vector C. Assume that's vector B. Let's draw a parallel pipe determined by these 3 vectors first. Assume that the parallel pipe is determined by vectors a, b, and c. Assume that the parallel pipe is determined by vectors a, b, and c, and assume the base of the parallel pipe is determined by vectors b and c. Now, if we compute the cross product b cross c, then what do we get? So let the parallelogram determined by vectors b and c be the base of the parallelogram. If we compute the cross product b cross c, what do we get? Then the vector b cross c is perpendicular to the base. This vector b cross c is perpendicular to the base of the parallel pipe. So if I compute the cross product b cross c is perpendicular to the base of this parallel pipe. Because cross product generates a vector that's perpendicular to both vector b and vector c. So this vector is perpendicular to the base of this parallel pipe. And the absolute value of b cross c represent the area of the parallelogram determined by vectors b and c. By the previous theorem, magnitude of vector b cross c represent the area of the parallelogram determined by vectors b and c. Area of this parallelogram, which is the area of the base of this parallel pipe, which is the base area of the parallel pipe. So the base area of the parallel pipe is the magnitude of b cross c. we know that the volume of the parallel pipe is base area times the height. Volume of a parallel pipe is always the base area times the height. Now we know the base area of the parallel pipe is magnitude of the vector B cross C. This is the base area we just found it here. That's the magnitude of B cross C. That's the area of the parallel pipe. Next, we try to find the height. Next, the h being the height of the parallel pipe. The h being the height of the parallel pipe. Now let me show you h in the picture. The h being the height of the parallel pipe. Then this side will be h. This is the height of the parallel pipe. And let theta be the angle between vectors B cross C and A and B cross C. Let theta be the angle between vector A and B cross C. This is theta. Theta is the angle between vector A and vector B cross C. Since vector B cross C is perpendicular to the base, then h lies on this side. H lies on the side B cross C. We can measure h from this side. Since this vector B cross C perpendicular to the base of this parallel pipe, so we can measure h from this side. Then in this triangle here, h is the adjacent side. A is hypotenuse. H is adjacent. A is hypotenuse. We know that hypotenuse over adjacent over hypotenuse is cosine. So cosine theta is hypotenuse over adjacent. Adjacent over hypotenuse. Refer to this triangle. H is adjacent. A is hypotenuse. Cosine theta is adjacent over hypotenuse, which is h over magnitude of vector A. Then, if I solve this equation for h, I can write h as vector A times cosine theta. I can write h as magnitude of vector A times cosine theta. But the thing is, cosine theta sometimes is positive, sometimes it's negative. Cosine theta sometimes is positive, sometimes it's negative. There's no guarantee. But h is always positive. In order to guarantee h positive, we must take absolute value. In order to guarantee h to be positive, we must take absolute value. H is always non-negative. Height cannot be negative. Then we must take absolute value. Magnitude of A is always positive, so don't worry about it. But cosine may be negative, so take absolute value for cosine. Magnitude of vector A is always positive. We don't need to take absolute value. But cosine theta sometimes is positive, sometimes it's negative. We must take absolute value for cosine theta. Otherwise, the height may be negative, but height cannot be negative. In order to guarantee the height to be positive, we must take absolute value for cosine theta. So, the volume of the parallel pipe, if I plug in H here, the volume of the parallel pipe is base area B cross C times A times absolute value of cosine theta. It can be rewritten as, I can take absolute value for the entire expression. Absolute value of magnitude of vector A times magnitude of vector B cross C times cosine theta. Then take absolute value. I can multiply the number first, then take absolute value. Then this is one vector, that's another vector. Theta is the angle between A and B cross C. Theta is the angle between A and B cross C. Then by a theorem from previous section, this is the dot product A dot B cross C. This is the dot product of these two vectors, A dot B cross C. Because from previous section, we learned a theorem that says vector A dot B, that's the same as magnitude of vector A times magnitude of vector B times cosine theta. So here I can treat A as A. B cross C is a vector. I can treat this as B times cosine theta. Theta is the angle between these two vectors, between A and B cross C. Theta is the angle between these two vectors. Then they're equal to the dot product of A dot B. They're equal to the dot product of A dot this vector. So let's complete the proof. The volume of the parallel pipe is always, the volume of the parallel pipe determined by vectors A, B, and C is always the absolute value of vector A dot vector B cross C. Let's complete the proof. Next, let's try a simple problem. Let A, B, C be vectors in R3. Let A equal to 3, negative 5, 1. B equal to 0, 2, negative 2. And C equal to 3, 1, 1. Be vectors in R3. Find the volume of the parallel pipe. Determined by vectors A, B, and C. Let A be 3, negative 5, and 1. Let B be 0, 2, negative 2. And let C be 3, 1, 1. Be vectors in R3. Find the volume of the parallel pipe determined by vectors A, B, and C. So, use the previous theorem. volume of the parallel pi p determined by three vectors a, b, and c is always the absolute value of a dot b cross c. So we compute the cross product first, then take dot product, then take absolute value. Let's compute cross product first. For b cross c, first of all, write the standard base I, j, and k in the first row. Then write vector b, write the component of vector b in the second row. We have 0, 2, negative 2. Then write the component of vector c in the third row. We have 3, 1, 1. Then compute the cofactor expansion. We have I times determinant of the matrix 2, negative 2, 1, 1 minus j times determinant of the matrix 0, negative 2, 3, 1 plus k times matrix k times determinant of the matrix 0, 2, 3, 1. Then find determinant for each 2 by 2 matrix. We have I times 2 minus negative 2, which is 2 plus 2, minus j times 0 minus negative 6, plus k times 0 minus 6. And write the answer in vector form. I have vector 4, comma, negative 6, comma, negative 6. That's the cross product, B cross C. Next, compute the dot product, A dot B cross C. Vector A is vector 3, negative 5, and 1. Vector B cross C is 4, negative 6, negative 6. Then compute the dot product. 3 times 4 is 12. Negative 5 times negative 6 is positive 30. 1 times negative 6 is negative 6, which is 42 minus 6 is 36. So for the volume, we take absolute value. Volume is absolute value of A dot vector B cross C, which is absolute value of 36. Absolute value of 36 is the same as 36. That's the volume of the parallel pi p, determined by vectors A, B, and C.